Manipulable cone-based bare hand object selection in high occlusion virtual environment. We propose MCBOS, a manipulable cone-based bare hand object selection method in VR scenes with high occlusions. Our method constructs a manipulable cone allowing users to manipulate virtual objects within this cone using their bare hands, exposing occluded target objects for selection even in highly occluded situations. MCBOS significantly improve the efficiency and utility of object selection than the SOTA methods. Manipulable cone. Based on a two-bend camera model, the manipulable cone is constructed. CM has three parameters: the apex V, which is initialized by using the user viewpoint, the base center point PM, which is initialized with a constant, and the radius RM, which is set to 20% of the height of the screen. CM corresponds to the main camera in the two-bend camera model. Next, we also constructed the auxiliary cone CA with three parameters: the apex V, which also uses the user viewpoint, the base center point PA, which is set to 80% of the base center point PM, and the radius RA, which is calculated by the apex V, the base center point PM, the base center point PA, and the radius RM. CA corresponds to the auxiliary camera in the two-bend camera model. Manipulation of the manipulable cone is in two stages. In the first stage, we can use hand displacement to control the direction of the manipulable cone. In the second stage, we can use hand displacement to control the apex VM of CM to achieve the effect of using two-bend camera to occlude and expose the target object. Manipulable cone-based interaction design. Our method uses three primary gestures: toggle, slide, and select. When the toggle gesture is first detected, the manipulable area selection state is entered and the user's hand turns yellow. After the gesture is released, the manipulable cone becomes active. PM of manipulable cone is controlled by the displacement of hand, which indicates the manipulable area inside the inner circle. When slide gesture is detected, the manipulable area is locked. To enter the de-occlusion state, the user's hand in the manipulable area turned green, and the hand displacement is used to control the apex VM of the manipulable cone to achieve the de-occlusion effect. When the user releases the slide gesture and enters the resting state, the user's hand in the manipulable area will turn red, and the hand displacement is unbound from the manipulable cone. Users can continue to use slide gestures to manipulate the VM of the manipulable cone to get the best occlusion effect. When the select gesture is detected, the selection state is entered and the user's hand and manipulable area turn blue. The user hand is displaced and unbound from the manipulable cone. The control pinch point is located on the target object and the select gesture is released, completing a selection. When the selection is complete, the manipulable area is unlocked and the user can proceed to the next area manipulation. User study. In the user study, we designed a target selection task for the participants. They were required to select 5 randomly appearing red objects in the scene, one at a time. We designed a total of 4 different scenes, incorporating 2 levels of object density and 2 levels of object distance. Our user study included 3 conditions. Condition 1 is the 3D bubble method, which requires high precision in hand movements. In high occlusion environments, it is challenging to accurately control the bubble to the desired object. Therefore, using this method, we can only select objects by moving our position to expose the occluded objects to the field of view before making a selection. Condition 2 is the multi-bubble method. This method increases the number of bubbles, providing multiple candidate bubbles simultaneously. However, it still suffers from the issue of objects jumping between the hand and the bubbles, and the multiple bubbles colors can interfere with our judgment during selection. Experimental condition is the MCBOS method. In high occlusion environments, we can use MCBOS to remove the occluding objects in front of the target object. This method fully exposes the occluded objects to our view, significantly increasing selection accuracy and greatly reducing the precision requirements for gesture recognition. Results. We evaluated the objective performance of these 3 methods using 4 metrics: completion time, error rate, total rotation, and total translation. The results showed that MCBOS significantly outperformed 3D bubble and multi-bubble in all 4 evaluation metrics in high object density scenes. Moreover, our method achieved significant improvement in completion time, total rotation, total translation in the low-density scene. In terms of subjective metrics, we first evaluated these 3 methods using the NASA TLX questionnaire. The NASA TLX questionnaire indicates that MCBOS shows significant improvement over 3D bubble and multi-bubble across all metrics. Secondly, we evaluated these 3 methods using the UEQ and SSQ questionnaire respectively. The results of the 2 questionnaires indicate that, without compromising perspicuity, MCBOS shows significant improvement compared to 3D bubble and multi-bubble. In conclusion, we have proposed MCBOS, a manipulable cone-based bare-hand object selection method for high occlusion virtual environments. Compared to the state-of-the-art methods, our method significantly enhances efficiency and utility.